The conventional perception of narrow diameter implants may need to be reconsidered. Some implant manufacturers claim that narrow diameter implants possess sufficient strength and can function predictably over the long term. In some cases, they even suggest that implants with a diameter of 3.3 millimeters can be used in posterior regions. But why do clinicians choose narrow implants in the first place? There are three primary reasons. 1. To avoid defect formation. In a thin ridge, defects such as dehiscence and fenestration can easily occur. Therefore, there is a tendency to choose a smaller diameter fixture to avoid the occurrence of defects altogether. 2. To maintain a stable crestal bone level. Spray et al. Reported in Clinical Oral Implants research that maintaining approximately 1.8 to 2.0 millimeters of buccal crestal bone around an implant was associated with improved long-term bone stability and reduced gingival recession. This concept remains an important clinical guideline today, leading to the trend of selecting smaller diameter fixtures in thin ridges. 3. To simplify the surgical procedure. Selecting a smaller diameter fixture in a narrow ridge can simplify the drilling sequence and minimize additional procedures, such as GBR or bone grafting. Consequently, narrow diameter implants have been preferred for clinical convenience and simplicity. With the widespread use of internal connections, the fixture's top rim has become thinner, exacerbating structural limitations in narrow implants. Although external connections offer higher strength, they cause more crestal bone loss at the implant abutment interface due to biologic width. Consequently, internal connections remain the standard today for their biological advantages and clinical ease of use. Anitua and colleagues reported that wider implants may provide more favorable force distribution, whereas narrow diameter implants may present biomechanical limitations due to reduced fatigue resistance. Jalk et al. Reported that repetitive loading can lead to fatigue damage accumulation in thin implant walls, which may contribute to implant failure, and that increasing material strength alone may not fully overcome these biomechanical limitations. This is because titanium itself is inherently a relatively soft metal. Although its strength can be enhanced through manufacturing processes, there are clear limitations to increasing strength enough to completely overcome the biomechanical disadvantages caused by a reduced diameter. In addition, recent finite element analyses conducted by MegaGen's R&D Center on Grade 4 cold work titanium implants with 11-degree and 5-degree internal connections demonstrated that smaller implant diameters and thinner wall thicknesses can result in greater microdisplacement under high masticatory forces. The analyses also suggested that microdisplacement exceeding 10 micrometers may induce plastic deformation of both the thin fixture wall and the implant abutment connection. In other words, even if the strength of a narrow diameter implant is enhanced, it may not represent a fundamental solution for sites with insufficient ridge width. Over time, selecting an implant diameter that is unable to adequately withstand occlusal loading may lead to biomechanical limitations and increase the likelihood of various mechanical complications. Although many companies are developing thinner and stronger implants, clinicians should not rely solely on the concept of thin but strong. In posterior regions with high masticatory forces, ensuring long-term biomechanical stability with an adequate fixture diameter should remain the top priority. When encountering a thin ridge, the MegaGen Blue Diamond system allows the selection of fixtures with diameters of at least 3.7 millimeters in premolar regions and 4.1 millimeters in first molar regions, where biomechanical strength has already been clinically validated. These diameters can provide sufficient biomechanical stability under the expected occlusal loading conditions. However, if a narrow ridge predicts defects unmanageable by the Blue Diamond system alone, GBR or bone grafting becomes necessary. Yet as noted, these procedures are difficult, costly, time-consuming, and prone to bone resorption over time, causing further complications. Could there be a more biomechanically manageable and surgically simplified approach? When encountering such cases, the BD cuff implant system, featuring a machined cuff and the contourization concept, can serve as a novel approach that maintains sufficient functional strength while reducing the burden of GBR. Let's look at the clinical application concept of the BD cuff implant system. The first step is to select a fixture diameter that can reliably withstand the expected occlusal load at the implant site. Especially in regions expected to receive high posterior loading, such as the first molar area, the BD cuff implant system, as it is based on the biomechanically validated Blue Diamond design, allows the preferential selection of implants with diameters of 4.1 millimeters or more. Any defect from implant placement can be managed using a machined cuff matching its vertical extent, transforming the area into a thread-free zone. Then, the contourization concept ensures sufficient horizontal soft tissue thickness to maintain biologic stability. This machined cuff-based soft tissue management concept of the BD cuff system is also well aligned with the zero bone loss concept proposed by Thomas Linkevicius. Although further follow-up is needed, osseointegration does not occur on the machined surface, allowing an adequate peri-implant soft tissue zone to develop and support the formation of a stable biologic width. This may help reduce bone loss around the threads, supporting a more stable biologic environment. Ultimately, by enabling more stable distribution of occlusal forces through an adequately sized fixture, this approach provides a biomechanical advantage while minimizing the need for GBR or bone grafting, offering benefits in both surgical simplicity and long-term stability. Therefore, narrow-diameter fixtures should not be viewed as a universal solution for long-term stability in posterior regions. In posterior implant dentistry, the first priority is not defect avoidance, but the selection of a fixture diameter capable of achieving sufficient biomechanical stability. The BD cuff concept represents a new strategy that addresses this stability in a more biomechanically and biologically manageable and surgically simplified manner. Narrow diameter is not the answer for thin ridges. Long-term biomechanical stability should come first, and BD cuff provides a simpler path to achieve it.